Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we reanalyze the data coming from the experiment where the effect of honey on hemoglobin levels was studied. So let me remind you what we had, and then I'm going to tell you what are the change that we are going to be considering here, right, in this video, how we are going to be extending what we have done thus far. So remember that's the example I'm referring to, right? We had 4 pairs of twins, right? One of them, one twin from each pair was assigned to the treatment group, meaning those 4 twins, right, included honey in their diet, and then we had the control group. So each, one twin from each pair was assigned to what we could call the control group, no honey in their diet, and then the increases in hemoglobin levels were compared. Remember? And in that case, what we have done thus far with this data set to analyze it is we considered 5 different scenarios, right? And each of these represents a scenario that could be indexed or identified by the proportion of honey twins that see an increase in hemoglobin, right? The percentage of them that sees an increase in hemoglobin levels. Make sense? Okay. Well, a greater increase than the control group. Make sense? So we had that data, right? That was our data. And then we thought about it from the perspective of our Bernoulli trial, right? We either have a success if the honey twin sees a greater increase, or a failure otherwise, right? So what we saw is that we could analyze the entire sample of 4 observations using a binomial likelihood. Remember that at some point we saw what happens if we analyze the data sequentially, meaning one observation at a time, and then what happens if we analyze this data set but using the entire sample. And to use the entire sample, we used a binomial distribution as a mathematical model for the likelihood, right? And then using that approach, we ended up with these posterior probabilities, right? So these likelihoods come from using a binomial distribution, right? Remember? Okay. So, as we have seen already, right, in Bayesian statistics, parameters, right, in this case, the proportion of honey twins that were going to be seeing a greater increase in hemoglobin levels, right? In this case, the parameter, that proportion is the parameter of interest, right? And in Bayesian statistics, parameters are considered random variables, right? So the main ingredients to do Bayesian statistics are the following: a prior distribution for that parameter of interest, in this case a prior distribution for the proportion, a likelihood that is can be thought of as a conditional probability where what we obtain is the probability of observing our data given a particular value of the parameter, right? And then to find the posterior probabilities, right, what we do is we apply Bayes' theorem. Okay, so let me summarize the Bayesian approach here and the way that we did it in this particular case, and then I'm going to underline the change that we are about to introduce in this video. Okay, so we said what we have is a parameter of interest. In this case, let me use the letter pi to refer to that parameter of interest, which is a proportion. Now, again, the basic ingredients are we need a prior distribution for pi, and that prior distribution, let me refer to that guy as p of pi. Okay, so what we did here, right, what we had in this particular example was something like this. We had the following prior distribution. So we were just considering the following values. That proportion could be 0, that proportion could be 1/4 or 25%, that proportion could be 1/2 or 50%, then 75% or 3/4, and finally that proportion could be 1. Okay, and we had at first we were considering that each of these values were equally likely. Okay, so that was our prior. Then our likelihood, the other important component to do Bayesian statistics. Our likelihood, which in our notation here with that p would be the probability of observing our sample given a particular value of the parameter of interest, right? In that case, it was given by a binomial, right? A binomial distribution. So n factorial divided by y factorial times n minus y factorial times pi to the power y one minus pi to the power n minus y. Right? Okay. And our posterior distribution which it's going to, this posterior distribution, it's going to reflect the information coming from a sample, right? Empirical evidence, right? To revise the initial assignment that we had here, the initial probability assignment that we had for each of the possible values of the parameter of interest. Okay, so this guy is going to be the probability of each particular possible value for the parameter of interest, given that we have observed a particular sample, right? So what we know is that we can find this guy using Bayes' theorem. So in this case, what we have is our prior in the numerator, right? Prior times likelihood and then we divide, right, by that product, by all those products, right, for all values of pi, right? So in this case we have 5 values, right? 0, 25%, 50%, 75%, 100%, right? So for all values of pi, right? Okay, so now that we have summarized what we have done so far, right, the change that we are introducing in this video, the kind of extension, kind of a new idea, right, is, hey, what if instead of having a prior distribution for pi, that proportion being a discrete probability distribution with a finite number of possible values, right? What if we wanted to consider a prior distribution for pi in an interval? So for instance, in the 0-1 interval, right, we are interested in considering any possible value for that proportion between 0 and 1. Okay, so that's the change that we are going to be considering here. Make sense? Okay, so a first step in that direction, right, if we wanted to consider any value in the interval 0-1, would be an extension of what we have here, right? So we are assuming that any value here, any of these 5 values, is equally probable, right? So think about a model that you have seen before, where you have the same probability for any of those values between 0 and 1, an extension of something like this. So if you think about it, that model, now let me get rid of this guy, or well, I'm going to be copying this in another file. So let me just say this was before what we're going to be doing now. So again, we're going to be interested in the same parameter, a proportion, but now we would like to consider the following prior distribution. Okay, how about this guy? 1 if pi lives between 0 and 1, and let's include 0 and 1. Okay, So you have seen something like that before, right? So let's quickly make a graph of what that probability density looks like. So what we're saying is we have all values between 0 and 1. Let me create a sequence here from negative 0.5 to positive 1.5, distance between each of these guys 0.001. Okay, now it turns out that if you take a close look at this guy, you'll see that, oh yeah, this guy is a continuous uniform, right, in the interval 0, 1. So to make a graph so you can see it, it's going to be just a horizontal line, right? You guys agree? Anyway, so it turns out that there's a function in R, right, that allows us to evaluate the PDF of uniform, and that function is the unif, okay, as in density. So the default is that the minimum is 0 and that the maximum is 1, so that's okay. So I would like to evaluate the PDF for a uniform 0, 1, a continuous uniform in 0, 1. Now to make a plot, kind of a scatter plot, to make a graph of the PDF, I'm going to be using the function plot. First we need the numbers that we're going to be using for the x-coordinate, for the horizontal axis, then the numbers that we're going to use for the vertical, for the y-coordinate, and then let me use PCH equals 19 because I would like to see solid circles. Okay, so you have seen that graph before, for instance in sta360 you have seen it. So 0 outside the interval 0, 1, and 1 if we are inside that interval 0, 1, right? Okay, so anyway, that's the guy that we want to consider, right? So now we are considering any proportion between 0 and 1, and you know, these guys, I mean, what we're doing here is this guy, this PDF is reflecting that we are open to any possible value and that we believe that all of them are equally probable. Okay, so this guy is what we in Bayesian statistics call vague prior. Okay. So going back to what we did before, our likelihood is going to be the same. Okay, now how our posterior is going to change, we're going to see that in just a sec. So let me copy this. The likelihood is going to be the same as it was before, the other ingredient. So now take a look at this. Let me call this guy, right, the numerator. This is just the product between prior, right? Let me write it down like this: prior times likelihood. And well, let me just copy this denominator like that here. Okay, but if you think about it, what we have here is the sum of all those products of prior times likelihood. So let me write it down like this. Okay, so we would like to compute something like this and generalize that idea of finding a sum for all values of pi, the proportion. Okay, so posterior distribution, And let me, in this case, just say that this would be the same as a numerator divided by a denominator. Okay? Okay. So let's find that posterior for that particular case. Well, not particular case. Sorry, for that extension. So posterior. Let's find that numerator first. We know that the numerator is prior times likelihood. So meaning this guy times this guy. So our prior is so nice because it's just a 1, right? So when we multiply this times this, well, our numerator is just this guy. Right? Agreed? So that's our numerator. In our particular case, remember that what we saw is that we had, let me find that, let me go back to the data that we had when we thought about it like this, right? What we did here is we thought about it in terms of a proportion of blue chips, right? So anyway, so what we saw is the number of blue chips in our sample. So in that case, y was equal to 4, right? So in our particular case, right, what we had was n, the sample size was 4, y was also 4, so we ended up with 4, and this was 0 factorial, right? And then pi to the power 4, 1 minus pi to the power 0, right? So in the end, the numerator is just pi to the power 4, right? This is just going to be a 1. 0 factorial is 1. These guys cancel out. This is just a 1. So that's our numerator, pi to the 4th power. Make sense? Now, let's talk about that denominator that we need to find to obtain our posterior. So it's the sum of all these products, right? For all possible values of pi, okay? So, what we need here is the sum of all possible products of prior times likelihood for all possible values of pi. But now pi lives in an interval from 0 to 1. So what we're going to be doing to find the denominator is now, instead of a sum, what we need is an integral, right? We're going to be computing the sum for all possible values between 0 and 1, right, of pi times, well, of the prior times the likelihood, and we're going to be doing that sum with respect to the values of our proportion, pi. Okay, so in this case what we need to do is finding the integral from 0 to 1 of pi to the 4th power, right? So that's not too bad. So that is just going to be, you know, pi to the 5th divided by 5 and then we have to evaluate here, right, when we have 1 and 0. Yeah, let me make it like this. It's going to look nicer. Okay, so that is clearly just 1 over 5. Make sense? So bottom line, what I wanted you to see here is that when we go from a discrete prior, what we had before, that considers a finite number of possibilities for our parameter of interest, pi, right, and we go and extend that idea to a variable, to a parameter where we consider you know, an infinite and continuous interval, right? The idea is that to apply Bayes' theorem, instead of using a sum to compute that denominator in Bayes' theorem, we're going to be using an integral. That's basically the idea, right? Okay. So our posterior is just going to be numerator divided by denominator, right? So finally, right, our posterior will be just this. Finally, posterior distribution, meaning, let me use that notation that we had before, our posterior, which is probability of pi given our sample, right? And this, what we said, is just you know, our numerator divided by our denominator, so it's going to be this guy divided by this guy, right? Pi to the power 4 divided by 1 over 5, so this happens to be just 5 times pi to the 4th power. Now this is a probability distribution, right? So we need the support, and the support is clearly any proportion, any pi between 0 and 1. Now it would be a good idea checking that we ended up with a legit probability distribution, right? Checking. So we know that legit probability density functions should be non-negative, meaning 0 or positive. So in this case, this guy is going to be 0 if the pi that where we are evaluating is not inside the 0-1 interval, and it's going to be 5 times pi to the 4th, okay, if pi lives between 0 and 1. Okay, so first condition checked is a non-negative function, so it's 0 or positive, right? Second condition, the integral from negative infinity to infinity of legit PDF must be 1. So let's check that that integral is 1. So in this case, let me be lazy, because the only part that matters is the interval 0, 1. I know that we have to check between negative infinity to infinity. If we do that, then it's going to be okay, let me just be super specific. So this guy is going to be 0 otherwise, and then we want to check that the integral between negative infinity and infinity of this guy is 1. So what I mean is that outside the 0, 1 interval we're going to have 0, so the only part that matters is the integral from 0 to 1 of 5 pi to the 4th, and that's easy, right? That's just going to be 5 times pi to the power of 5 divided by 5, and we are evaluating this guy here. We will have 0, 1, 0, 1, so clearly we're going to have 1 over 5 times 5, that's going to be 1. So this is a legit probability distribution, right? A legit probability density function. Okay, so finally, one extra. If we wanted a point estimate for that proportion of interest, point estimate, well, one option, and we're going to see in the future, right, we're going to justify that it makes sense to use the following quantity as a point estimate for a parameter of interest from a Bayesian perspective. If we wanted a point estimate for pi, well, a good choice would be the posterior mean, meaning the expected value of the posterior distribution. Okay? So in this case, it would be just the expected value of that probability density function, right? Okay, so let's find the posterior mean. Well, since in this case we have a continuous random variable, right, it would be the integral from 0 to 1 of this guy, the PDF, but we need that integral. Well, first, let me say just something. It would be, if we're going to start from the definition, it would be the integral from negative infinity to infinity of pi times your posterior distribution, right? And we're going to be integrating with respect to pi. We know that the only region that matters is the 0, 1 interval. So in the end, what we have is just the integral from 0 to 1 of pi, well, 5 pi to the fifth, right? That's what we're going to end up with, because we're multiplying by pi, right? So 5 pi to the fifth. Oh, come on. It's kind of ugly. Why? Won't do it for me. Let me retype this one. No, that's fine. You know what I mean. Oh, that's better. Okay. So that's going to be just, you know, once you do the calc, it's going to be just 5 times pi to the sixth divided by 6. And we're going to be evaluating in this interval 0, 1, right? Uh, 0, 1, okay. So in the end, we have 5 over 6. That would be our point estimate for that proportion, right? If we wanted a point estimate, okay? Okay, let's summarize what we did here, right? The basic idea of what we, well, the main ideas that we discussed here are these. So first, we underlined that in Bayesian statistics, parameters are random variables, okay? So, and that the main ingredients to do Bayesian statistics, to do Bayesian inference, are these. A prior distribution for the parameter of interest. Again, this guy is going to have a distribution, a probability distribution, because we're considering this guy a random variable. So prior distribution, that's one of the ingredients. The other one is the likelihood. So in this case, the new idea or the extension that we discussed here is that our prior distribution now includes not a finite number of possible values for the parameter of interest, but now this guy takes values over an interval. Okay, so since we're talking about a proportion, it makes sense that they take well, the possible values for that proportion are numbers between 0 and 1, and the first continuous distribution that we considered here for that extension was the uniform. Okay, the likelihood, for our experiment, it made sense to use a binomial, right? And then to find the posterior, what we do is, just like before, we use Bayes' theorem, right? Now, the difference between the version of the Bayes' theorem that we had before and the one that we have now is to find the numerator. That's the same, that's a product of prior times likelihood, but to find the denominator, that's where the difference lies, is now the law of total probability looks like this. Instead of a sum, we have an integral. Okay, but then the idea is the same. Okay, and we also just you know, as an extra, we mentioned that if you wanted to provide a point estimate for your parameter of interest, a good option would be reporting the posterior mean, which is just, the expected value, what you have seen before. Pi times, in this case, the posterior distribution. That's the density that you're using to compute that expected value. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.